Hey, Dr. Clark, back at you here in Chapter 9. In this section, Section 2, we're going to really learn how to do multiple mean tests with quantitative data. The first section, it was really kind of getting the idea, how does this work, and we use the MAD statistic. Section 2, we're going to learn the real statistic, which is called ANOVA, and I think you're going to find this very interesting. Let's get started. So when we're comparing more than two means, what it's typically called is ANOVA, which is an analysis of variance is what that means. And what we had last time with the MAD statistic, we were able to compare whether two groups had the same average or different average. And then if you had multiple groups, then we sort of averaged all those differences together. But what happened was this did not really take into account the sample size of each group. We just looked at the averages, right? And so that's actually a pretty big problem, because it should be the case that the bigger the sample size, the stronger the evidence, right? If there was a difference. And that just isn't the case with the MAD. So we need something better. And what that thing is called ANOVA. Okay? The statistic is called the F Statistic. And it's similar to when in Chapter 8 we had the chi-squared statistic, was what professional statisticians used. Well, now we're going to use the F statistic. And it's going to incorporate both sample size, but also the variability within each group. Remember, when you have quantitative data, there's the mean of that group, but there's also the standard deviation. And so it's going to factor in the mean, the standard deviation, and the sample size, all to give us one thing. You're not going to have to do this yourself. The applet is going to do it for you. But the idea of what the F statistic is it looks at the variability between groups and divides by the variability within groups. And you'll remember the T statistic from when we did two means. We subtracted the two means. Well, that would be the variation between groups. How much was group 1's mean different than group 2's mean? And then we divided it by this formula for the standard deviation, which included the standard deviation and also the sample size, but it combined them because there was two groups into one number that measured how much variation is there happening inside of each group. Well, it's going to be very similar to this, but now there's going to be more than two groups, so it's going to have to be more complicated. And we're just going to let the applet do it for us, but this is the idea that you can take away. We're comparing how much variation is there from group 1 to group 2, and then dividing that between how much sort of standard deviation is happening within the groups themselves. Okay? And yeah, so we're looking at differences in the sample means. We factor in the standard deviation. We don't need to know the formula, but the key idea is the bigger the F statistic, the stronger the evidence against the null hypothesis. And so the null distribution is going to be one of those shoe distributions with a long tail to the right, but stops at 0, and so bigger is stronger evidence. All right, when you're setting up the hypotheses, it's going to be very similar to what we talked about in Section 1 of Chapter 9. The long run or population means are the same. Either they're all the same, or there's no association between the explanatory variable and the response variable. Or at least one of them is different. And so the F statistic that we're talking about, this ANOVA test, what it's going to do is it's going to find out, do we have evidence that all of these means are the same, or do we have evidence that at least one of them is different? If one of them is different, of course, we can follow up with confidence intervals and see, comparing each pair, you know, this one to that one to this one, etc., to see if there's any that are different. You know, we know this one's bigger than the rest, or something like that. There are validity conditions, because this is a theory-based test now. There's really two. One is the sample size, which we've seen before for quantitative data. You want to have a sample size of at least 20 in each group, and you don't want to have strong skew. Right? That's kind of the standard condition for quantitative data to do a theory-based test, but now there's more than one group, so you want that to be true for each group. There's a little caveat here. If you have, say, maybe only had 18 or 16 or something, but the data was very symmetric in each group, you can probably get away with using an F statistic. So there's a little bit of wiggle room here, but this is really what you'd like to have, is at least sample sizes of 20 and no strong skew in the data. If you had a smaller size sample, but you had nice symmetric data, then you'll probably be okay. But there is a second condition, and that's called the equal variation. Because we are comparing this variability within groups, there's those standard deviations inside of each group. Well, you can't have those be too different from each other. You can't have group 1 have a standard deviation of 50 and group 2 have a standard deviation of 2. That breaks the statistic, or at least the assumptions that are going into how the statistic works. So the general guideline is you don't want the largest standard deviation to be more than twice the value of the smallest. So if one standard deviation is 3 and one standard deviation is 5 and one standard deviation is 4, that's okay. But if one was 3 and one was 7, then you might have some questions about whether the validity conditions were met for doing the ANOVA test. Okay, so that's the main setup for this ANOVA test, at least all the theoretical ideas. In the next video, we're going to do an example. We'll see how to use the applet to actually conduct a test, and then how to interpret the results. So we'll see you in the next video.